Morning. I'm going to shoot two videos on the idea of uncertainty. Really important in science, but really important in physics. It's all about knowing how good your readings are. So this is fundamental for things like physics, where you are studying the physical properties of things. I'm going to break it into two parts. So the first bit today is we're going to look at the uncertainty in measurement. And it doesn't matter what you're measuring or how often you're measuring or even what you're measuring with, every single measurement has uncertainty. An example is this, really great app, I don't know if you know about it, called What3Words, and it is designed to be able to give you your reference wherever you are for deliveries, for safety, for rescue purposes, to a 3 metre square. Now, our 3 metre square, that according to this we're in, has a little 3 words. So What3Words is the name, and that is unique to that 3 metre square. So it tells us that we're within that. But actually, I can see from here that it's actually not quite in the right place. And this circle, where it is trying to find us, gives us our uncertainty. It means that actually we're somewhere within that circle. So although it's saying we have a definite answer, which is this coordinate up here, what it's actually doing is behind the scenes there's some give or take in the measurements. And this is what we mean by uncertainty. And every single measurement has it, and no matter how good your instrument is, it's still going to have it. So what we're going to do is, I think the classic example that means most to most people is a stop clock. Okay, now our stop clock here has hundredths of a second. Okay, as it runs through, that's great. But that's the instrument with a resolution, remember that word from GCSE, a resolution of 100th of a second, so it'll measure the nearest hundredth, but you and your human reactions aren't that fast. So the fact that you've got to react and push the button means that this reading will be out. And if you take average readings over time, you'll find that most people's reactions are about a quarter of a second. So actually that reading, although it's very good, it's actually give or take about a quarter of a second. And that's just to stop it. If you're starting it and stopping it, that's 2 pushes. So that's 2 lots of a quarter of a second. So your reading could be half a second out. And straight away you can start to see that that means some readings aren't going to be very good. If you're measuring something really precisely and trying to get a really short time, then that won't work. So what we're going to do is really work through 3 kind of key principles to this. The first is you're not going to get away from it. You will always have this. The second one is that if you choose something with as large reading as possible, so a large resolution, then it should make your readings more precise. Yeah, it will give you more decimal places in your answer. So, if for example I wanted to measure some paper, well, I'd use several instruments. I could use vernier calipers, which are measuring pretty well to around about 50th of a millimetre. I could use a micrometer, which we can measure to 100th of a millimetre. Or I could just use a ruler. And actually, although the uncertainty in this, the measuring resolution is a millimetre, I can probably tell to nearest half millimetre, so I can get a resolution that's better than the scale on here. But to measure a sheet of paper, you might think, well, that's hardly the right instrument. Okay? The thickness of that piece of paper is much smaller than a millimetre. But I can use that and actually get a really good accurate value. So the technique to use is an actual measurement technique that's better. It's not about the instrument. That will improve the resolution, but actually what we need is to use a technique that's actually going to make it better. So let's take example, go back to the stop clock. I want to measure the speed, the time it takes for this to do one complete swing. Okay, so that's from one position to the other side and back to the same position. Now this will get smaller So that will actually make the measurements less precise. So what I'm going to use to start with is something called a fiducial mark. And for this would do, is a start-stop line. So I'm going to use that because it's easy to see when it crosses that. Okay. So I'm going to start my stop clock when it crosses the line, swings all the way back and goes back to the starting position. So that is one complete swing. The time period, the time for one oscillation, time for one vibration, the time for one swing. That time period we can measure from a fixed position. So I'm going to start it going because that makes it more accurate because I'm not trying to do two things at the same time. And then I'm going to start this and stop this as we go through. And there you go. I've got a time of 1.40. But realistically, that's give or take half a second. It's anywhere between 0.9 and 1.9 seconds. Okay? So ideally, if I'm going to be give or take half a second, I need a bigger time. So one of the main ways of getting a better measurement is doing multiple swings. Okay? So if I make that swing more cleanly, if I start it now and count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then what I've got, 13.55 is the time for 10 swings. If I divide by 10, my measurement will be 10 times better. I'll actually have a more precise value. So I'll have 1.355 seconds, which is actually quite close to the last one. But this is give or take half a second. If I divide the half second by 10, it means I'm actually measuring it to a much smaller uncertainty. It's a much better answer because I've reduced the measurement uncertainty by 10. Okay? If it had 20, it'd be twice as good again. 10 is just quite a nice round number because you can just move the decimal place. Okay? But 10 or 20 swings would be ideal. So we can do the same with these. Now I'm going to post some pictures of these and documents so you can see how to use this, but basically I have a 1.5 mm scale on the main axis, and that's my datum line down the middle, so that's where I take my reading. And then what I'm doing here is adding on hundredths of a second, so whatever lines up you'll get the reading from that. So for example, at the moment it's just over 5 millimeters, so to my mind that's 5.16 millimeters, so 1/1600th of a millimeter on top of 5. This one, again, we're going to use this in another experiment, so a big experiment fairly soon, which you need. Much more precise. Again, we've got the main scale. Ignore the inches along the top, but on the main scale along the bottom, we've got millimeters, centimeters and millimeters. And then on here, this bit that slides up and down, this is known as a vernier scale, and this will give you 50th of a millimeter. And all you're doing is looking for whichever number lines up, and it actually gives you a result. Now I think calipers are great because they actually can take several measurements. You can measure the thickness of something, you can measure how far things are apart, so you can measure the width of a hole, for example, and at the bottom end that also runs on the same scale, so it will tell you the depth of something, and again it's all read off the same scale, so they'll all give the same readings. So great instrument. So what I'm going to do is I'm going to take some readings, and I'm going to video this and slot this on the end. I'm going to do some different lengths, so we shall slide this up and down, okay? And in the very first experiment ever done, Galileo Galilei looked at pendulums and realised the pattern about it. Obviously, he didn't have a centisecond timer. He actually used his pulse, which again is very low resolution. If you're resting, it's probably around about 60 for most people. However, he could use it to get accurate results, and he actually came up with the mathematics that we still use today. So it's not about the measuring instrument, it's how you do it. The equivalent of this is that thickness of paper then. So if I take my thickness of paper here, well, I've taken it out of a packet, and the packet, one ream of paper, contains 500 sheets. So if I try measuring this on here, I'll probably find that it's almost unmeasurable. Okay, I reckon that's 0.06 millimeters, so 6/100ths of a millimeter. But if I take the whole pack, let me slide that out. Okay. And what I can do, I mustn't forget the one that I've taken out as well. What I can actually do is I can measure that result for the whole thick pad, and then what I'm going to do with that reading is I've got a much bigger reading, give or take a 50th of a millimeter, but much bigger. That 50th is tiny compared to that size, compared to what we had before. So with this reading, what we can do is we can actually write down and work out what the value is. So I'll do this one for you. It is 50, a shade under 52, so it's 51 points, looking at that, 0.96 millimeters. Okay, so that's the thickness for a ream. That's 500 sheets. So if I divide that by, I should say, plus or minus 0.02 millimeters, so that's my measurement uncertainty, a 50th of a millimeter. Okay, so that's how good my instrument is. And if I divide that by 500, then I also divide that by 500. Okay, and by doing that, I'll come up with a value which I can't do in my head, but it's looking fairly small. So in my calculator pack, I will do 51.96 divide 500, and that's going to give me something in fractions, of course, 0.104 millimeters, plus or minus 0.02 divide 500 equals 40 millionths of a meter, plus or minus 40 thousandths of a millimeter. Okay, so much more precise reading, a much smaller uncertainty, and I've got an accurate value for the thickness of a piece of paper. More importantly, the value for the average thickness of a piece of paper, because each piece might have different thicknesses. So for the whole pack in there, your average sample of 500 different sheets, that is our thickness. Okay, and that gives you a very good accurate value. So that is the key bit from this video, actually measuring techniques in a certain way, doing them in a way that will reduce that error is far more important than actually having a good measuring instrument. You know, I could measure that with a ruler, and that bit would be better, that bit would be worse, but I would still get that value, okay, even by using just a millimeter ruler. So the technique is really important, and that's what I'm going to get you to look at. So remember, there are certain things that you need to do. Timing is one of the worst things you can measure. Taking multiple readings, multiple swings, multiple layers, that's a much better way of getting readings. And the crucial bit, try and get the best instrument you can. Now there is one more point to consider, and again, it's whatever instrument. So for example, this measuring instrument at the moment, it's got a 0 error. There's nothing on it. So before you'd use it, what you'd need to do is re-zero it. Okay, so that will always give you better reading. Meter sticks, that one, it's slightly less than 50 centimeters because that's less than a millimeter at the end. You can see it's worn down. Our vernier micrometer is when I close it, again, I don't know if you can see it's so small, but it's actually half of a hundredth off. So I'd need to add that number onto every reading to make it really super accurate. Okay, but there's ways around that as well. But again, be aware of the zero error. So some examples for you. Have a go with these. I'm going to let you keep replaying this on the video. Try timing a single swing and then try timing different swings and see how that goes from there. Bit of practice for you to use your stop clocks. Simply use the one on your phone, it's perfectly good. Gonna measure the length, try different lengths, and the length, I should point out, has an uncertainty built in, but we're gonna do that on purpose. And the reason is we should measure the length to the center of the mass, which is almost in the center of the ball, but you've got this other bit as well. So there's quite a lot of errors that are unknown. So we're going to measure it to a very definite point. So what I've done is I'm actually going to measure it from the very top of the round surface. Okay, so if we get that running, and you can freeze and return on this video, measure the time for one swing, and then measure the time for multiple swings and divide by the number of swings. See which one gives you a better result. Now, it's always worth running through an experiment first. This one is the short end rather than a long end, and the reason I'm starting with that is this one is the quickest. So if you start with one that's quickest, you know how many swings you need to do to give yourself enough to time. I think even with this time, which is less than a second for a swing, you're probably enough for 10 swings. Okay, that would cover that. So if we then extend it down, okay, I'm just going to slide that down a bit more. Then this one, again, get the right length. We are going to measure that at 21.3. So if I change that measurement a second, 21.3, which is 0.213 meters, and that will allow you to get some precision in your reading. So again, you can see how many decimal places it is to make it accurate. So just going to do another 4 lengths after this, and what I'll get you to do is try repeating it, see whether time is longer if it's accurate enough just timing one. And even with the long ones, I don't think you'll find it's accurate enough. Okay, so you can get your second reading there, your third one, just again, bit of a length there, and again I'll put the results down underneath, 28.5, and I will record that at the same time. Again, there's enough swings there, and that's for that result. Okay, so you should be finding, even though there's some reasonable jumps in length here, the times don't tend to change much. So we'll do one more after this. So we're now on 34.1. Okay, so again, I'll write that down for you, but you can time away. Okay, so there's your length on that one. And there's enough swings. I don't think you needed to do 20 swings, so apologies if you had. Go back and just try 10 maybe, 10 swings per timing. and we'll do that as your longest, which gives us a reading in length of 43.2, almost a reverse of that. So 0.432, and that one I can't slot in at the same time. So again, much slower. That's going to be about 1.5 seconds a swing. Okay, so there's enough swings there to give you 10 readings. So use them, check out, do the maths of 1, do the maths of 10 swings, see how much it changes, and you should find that this uncertainty, although it doesn't change because that's your give or take 0.5 seconds, you'll find that your later readings get more accurate. If you try plotting it on a curve, on a graph, you'll find that it curves. The shape of the curve actually gets better as it gets longer. Why? Because your timings are better. Because you've got a nice big time, you'll find that they are more accurate because that smaller measurement uncertainty.